Okay, so I'm going to just briefly talk about some more advanced features in TensorFlow, which we have only used in indirect ways here. We did some of this stuff manually in the very first project, the pre-processing here. So there's a tf.data API. Uh, there's things called pandas and scikit-learn. Now, pandas we use to read the housing data right at the start. This can read a comma separated value uh, list of data and parse it. And scikit-learn can split the data into training and test sets. We used it to do this. Here it does defining test set is train test split is this function. And TF data is a powerful library, one of the lower level libraries. And this one here can actually handle huge data sets. Now, what we've done in this class is very simple machine learning exercises with very small data sets, like maybe a few thousand images. But of course, if you're really going to train the things like large language models, they have a huge data set, far too big to store in memory or on any hard drive. And so you have to read from multiple files in parallel and have all these fancy ways of picking just some of the items. And that's what this can do. Um, so TF record is the binary format that allows this. And you can define a series of data items. Now here, I just set them equal to print item right here, just range of 10. So I just have numbers from 0 through 9 stored here, but you can store any kind of data in there, and you can store a dictionary structure where you have a label of A, and that includes two tuples, each of which contains 3 items, and then B contains just 1. So you can have quite a lot of different kinds of data there. And you can repeat the input data. Batch will pick out a batch of instances. So here we're going to 3 times, we're going to do a batch of 7. And so here are 4 layers. I guess 3 times 10 makes 4 batches of 7, and there's 2 left over. Because, okay, I had a data of 10. I repeated 3 to make 30. So now I have 3 of each of those digits. And so if I do batches of 7, there's enough there to make 4 batches of 7 for 28 and have 2 left over. So this is how you might break things up into batches. And you can then chain these transformations. So here we have tensor slices, then we repeat it times 3 to make it bigger, then we run batches of 7, and that's what's going on here. And so you can do computations on the data with map to do things like double all the values, or keep only batches that satisfy the condition where the total is greater than 50. So it doesn't include the batch that included mostly low numbers. You can pull just a few items from the data set, pick 2 out of the data set, even though there were 4 lists of 7. And you can shuffle, of course, to randomly mix things. And there is a seed value, so you can make sure you're always going to get the same random numbers if you want to. So they often shuffle things if they're in some kind of order and you want to make sure you get a random sample. Then there's interleave, where you can read multiple files and interleave the instances to combine them together into a larger data set. And then there's pre-processing. We talked about this many times. If the data comes in different scales, like one item of data goes from, say, 1 to 10, and another one goes from like 1 to 1,000, then that will probably skew your machine learning by making the one with the larger scale be counted much more. So you often normalize things using the mean and standard deviation. So you just get the deviation from the mean divided by the standard deviation. So it'll pretty much be between -1 and +1. And that's the kind of thing you might do to make your data all at the right scale. And here's what it looks like when you combine all these things together. And you can also see it this way. So in you come a bunch of files. You then interleave them to make a data set. Then you cycle through them. You feed in more CSVs to create out of that. And then down here, you'd map it to change it in some way, like square it or something, then shuffle it, then batch it, then prefetch it. Those are the sort of steps you'll have just to pre-process data. And we did this manually for that California housing data that showed latitude and longitude and the price of houses, but you can automate it all with these transformations. And so prefetching will load the next batch while the current batch is training, so the CPU and the GPU are both busy. The CPU will be reading the hard drive and fetching data, and the GPU will be processing data. So that's improvement in efficiency. And so here you are. This is how you read it in with CSV. Then you train a model down here with model fit, and then you evaluate and predict. And you can make a custom training function if you want to, instead of using a standard thing like stochastic gradient descent. You can make it do multiple steps per execution, so it'll process multiple batches at once and other such advanced things by doing it with these more granular functions. And the TF record format is the preferred format for storing large amounts of data. And the point of this is you can have records of varying sizes, and they're binary, and each record contains length and a checksum, and then data, and then a checksum. So you can create a file here. You create a file with this name, and then you just write in some binary records. You can read a file, and this will be the output where it reads the file. And you can choose to compress it, so it'll zip it onto the disk and then unzip it when you read it, of course. And there's a thing called protocol buffers that specify the structure of it. So here I define an object called person that contains a string name, an int32 ID, and then a repeated string email. And that's what you have here. So that would store data like this: al123 and a@b.com. And so you can read them, you can modify a field, you can serialize it if you want to. So it has 1 byte string that has all this data formatted with, I think, line feeds to separate fields. And here's got this 1A separator, whatever that is. Anyway, it puts it in a serialized format, so you have 1 binary blob to encode a whole record. All right, and you can define the features here, listing what sort of data is stored, to specify the format of your data to be as general as possible. And so here you tell it, we're going to have repeated bytes, repeated float values, and repeated int64 to have lists of these things. And so this contains a person that has name, ID, and emails. And here it's allowing more than 1 value. So I have 1 name, 1 ID, and I have 2 possible emails. Each of these is allowed to have a list of items. And you can load them and print them out. So it's details of how you handle files and records. And they are layers in pre-processing to do this for you. So you have to normalize features to scale them to a standard scale, encoding categorical features, resizing images, and so on. You could do this yourself manually for data, but suppose you're going to keep retraining periodically with more and more new data that comes in the same format, then you might want to just automate it so you can feed in raw training data, and all the pre-processing is done by your pre-programmed system. So now when you add new, fresh data, you don't have to do any manual work. You can just feed it through the same pre-processing layers. And so you'd have you have the data of epochs go to your neural network, and then you have your production system here that is retrained as necessary on fresh batches of data. So one issue is a discretization layer. Suppose you have something that comes in like an age, but you really don't want to do any kind of math, like 2 people age 10 are equal to 1 person at age 20, or the people that are age 20 are twice as important as the people at age 10, or anything like that. It is a number, but you really don't want the machine learning model to think of it as a number and evaluate it as having the significance of a number. What you really want to do is think of it as categories. So you take age, and here you can just put it in, say, 3 bins: below 18, 18 to 50, and over 50. And then you'd have, it'll encode that as 0, 1, and 2. So that's putting it in bins, but you still have the problem that 0, 1, and 2 are still numbers, and the model may interpret 2 as twice as important as 1, and the distance between 2 and 1 meaning something, and a distance between 1 and 0 meaning something. And you really don't want that either. So what you really want is this. You want one hot encoding. You want to bin it into 3 bins, and then you want to encode it as just a 1 in 3 fields. It can be 1 or 0. Now you've just recorded you're in one of these 3 categories, but there is no meaningful numerical relationship or scale between the categories. That's why what one hot encoding is good for. And if it's something that can have, say, 2 properties at the same time, like age and something else, like whether they have a college degree, then you'd have 2 parameters to measure here. And it can be of any of 3 values. And so a person might have 2 of these properties, or only 1 of these properties, or a different set of 2 of these properties. So again, this separating these independent properties into different variables is the logical way to encode it. And they call that multi-hot encoding. Then you can have a string lookup layer, so I can feed in cities. Now here, it will just encode them as integers, and unknown things are coded as 0. So I think it just encodes them in the order in which they were defined or something. So it turns them into 1 and 3. Again, this is not the best because you don't really mean that 3 is 3 times as important as the 1. So one hot encoding would still be probably a better way to encode something like what city you're in. And you can have a hashing layer. Now, I think the point of these hashing layer is just for efficiency of processing. So it's not like an MD5 hash or SHA-1 where you'd really want it to be unique for every entity. It's just a way to randomly but predictably sort the data into categories. So here it has hash collisions. Tokyo is 1 and Montreal is also 1. So that's the kind of hashing you'd use in computer science for algorithmic speed, not the kind of hashing you'd use in, say, computer forensics, where you want a unique identifier of something. And then you have embeddings, which we were just doing with BERT. So if you had 50,000 words in your vocabulary, you could use one hot encoding. An embedding would be a smaller dense vector in something like 100 dimensions. So you start by initializing them randomly, and then you train them a gradient descent so it learns to put words with similar meaning near each other. And so you start with random locations, and then as you train it on the meaning, it will move to meaningful locations of these various things. And then you'll end up with meaningful things. So if you have a man and you find out how far away king is, if you start at woman and move that distance, you'll be close to queen. And that's the point. So not only are similar meanings near each other, but similar relative meanings have similar relative direction and length here. And that you can do with training, as we talked about before in BERT, by masking some of the words and having it practice predicting the missing word, and then masking sentences and having it predict the missing sentence. You can get it so it understands the context of word and can make an accurate vector of it. So if you embed a numerical field, data starts as random. And then you can chain 2 layers, string lookup, and then embedding. So you look up these strings, and then you go through an embedding to put them in vectors. And so then you have it, you vectorize it, and then you can go, that's one way, or you can use pre-trained language model components. And that's what we did in that project. We used a BERT pre-trained model to vectorize the words. So you split the sentences on white space, count the words, and numbers them with word IDs. And then you encode the word IDs somehow down here. One way to do it is rate them by how frequency the words are used, so that words that are rare in the document are uprated as being more significant than words that are common, like Z and A, that are all over the place but really don't mean very much. And then you can use things like pre-trained language model components. Here's one of them. That would this one encodes sentences as 50-dimensional vectors, and we used BERT that encoded words as 780-dimensional vectors, something like that. And we'll see that again as we go ahead. there are hubs like TensorFlow Hub out there that have pre-trained models available. And here's some of them like BERT and many others. And there's more of them on Hugging Face you can download. So there's open source models available to parse languages like English. And then you can pre-process images. You can resize them, you can rescale them, you can crop portions of them out, and you can do a lot of other things. You could do random crop or random rotation. All these things are available to modify images in whatever way you find desirable. And there is a datasets project that tries to gather datasets together so you have some things to practice on. We've used 3 or 4 common datasets here, but there are a lot more publicly available datasets to practice things on, like smartwatch gestures and so on. So that's all I wanted to tell you about this.